So good morning, everybody. This is the second webinar of the series on sensor systems and measurements. This is an Italian-German seminar series. My name is Matteo Pardo. I am with the Office for International and European Relations of the National Research Council, CNR. This is, as I said, the second of a series. The series will go on. I will tell you the third webinar, the topic, and the speakers of the third seminar at the end of this one. We are happy today to have Ulrich Krumbein and Simone Lolly with us. I'm very happy that we have many more participants, so almost twice as many participants as last time. We have 100 registered, not all of them participating, from different continents. We have two researchers from a Moroccan university, so we have Africa. We have researchers from a Malaysian university, I saw, and also a US company. So hopefully not participating from the US because now it's night. The seminar, the webinar will have the same structure as last time, which means that the two speakers will have half an hour to present the work or their sector, and at the end of each seminar presentation, you can ask questions. You have to write them down in the chat, which is on the right. On the right, you have as well under documents the two presentations. So the speakers were gentle. They were nice enough to send us the presentations in advance. So yesterday, so we could load them, and you can download them under documents, documenti. Okay, having said this, I will give the word to my co-organizer, which is Vincenzo Fiorentini, who is a science attaché at the Italian embassy in Berlin, who will say some words and introduce the first speaker, which is Ulrich Krumbein. Please, Vincenzo.
Good morning, everybody. Thank you, Matteo. So I'm, let's say, the German, the German side, so to say, in the organizing, in this small mini organizing committee. So and of course, as a science attaché of the embassy, I bring greetings from our head of mission, Ambassador Barricchio. So yes, our first speaker is Ulrich Krumbein. He has a PhD from ETH Zurich. He's a semiconductors expert mainly, and he has worked at Siemens and Infineon since 3 decades, more or less, almost. And he is now the head of the environmental sensing team. So that's what his contribution would be about. I think this is the idea of having somebody from industry is not only relevant because, of course, we all care about applications and real world downfalls of windfalls of research, but also because as I came to understand recently, in Germany, the quota of industry money going into research is preponderant. It's like 70% of the 3.1% of gross internal product that Germany invests in research. So it is there's a lot of effort in industry in actual research. It's not just application research. So that's why I think it's very interesting to hear from a voice inside one of the major actors in the semiconductor industry. Of course, as you know, Infineon exists since approximately 30 years, but Siemens has existed for 150. So it's a very important and very significant actor that we have to pay close attention to. So with that, I give the floor to Ulrich, and it's a great pleasure to have you. And we look forward to hearing what happens at Infineon
So you can see my screen.
Yes.
Yes. Then I go to presentation mode.
Fine.
Yep. Thanks a lot for the invitation. Really, it's a great pleasure to have the opportunity to show what we are doing at Infineon Technologies concerning environmental sensing. Maybe you know Infineon more as a producer for devices for automotive. That's the main part of what we do at Infineon. But we are have more directions where we are working on, and environmental sensing is something quite new. A couple of years we are working on this, and our idea and our mission is to measure what matters. And let's change the pointer, laser pointer, and then I go in. So there are sensors. We have quite some sensors in development and in production at Infineon. It's a broad sensor portfolio, and the goal is always to make our lives easier by synchronizing devices to human needs. So we have radar technology to mimic the touch, and radar technology to mimic the eyes looking. We have pressure sensors again on touch, quite very high precision. We have 3D sensors, microphones. We are the largest supplier in the world for microphones. So if you have a mobile, and you will have a mobile, there's a very high probability that microphones in your mobile will be from Infineon. And we are going into a new area, CO2 sensor. That's one part of what we are doing into environmental sensing. So this is again a view on this: pressure sensors, 3D technology based products, microphones, time of flight based. And the new part where we are in a couple of years, it's environmental sensing. Health concerns due to air pollution are growing and growing. Indoor and outdoor comfort and well-being is a topic we are looking into, and energy efficiency. Today it's we are all talking about energy, and we can do a significant contribution to reduce energy needs for HVAC systems, so ventilation, air conditioning, and to reduce the demand of energy in these areas. I will show later that this is really a significant amount. The focus of our environmental sensing is indoor-outdoor air quality sensing, and in future going into breeze, food analysis. The use cases are really large. There are a lot of interesting areas. What's missing often are really reliable sensors which can be used in these areas. So indoor CO2 is an important gas there. I will go for this. Outdoor ozone and NO2 are important gases there. There's this outdoor air quality index, and only if you can measure something you can change and improve the situation. And that's our goal, really, to create these sensors to improve the outdoor air, to sense the outdoor air. And then further new areas can be breeze and food analysis. There are asthma monitoring. There are a lot of areas, but it gets more and more difficult for the sensors to go into. So we start with the indoor and outdoor air quality monitoring, and have essentially we have two platforms, two differentiating technology platforms under development right now. One is a photoacoustic spectroscopy approach. I will go into detail more with the first lead product on CO2 sensor, which is just ramping right now. We are delivering the first samples there. Future platform extensions are there. And we have a second platform, which is a multi-gas adsorption type sensor. You see the concentration rate for the photoacoustic is larger than 100 ppm, and with this adsorption technology, we want to go into concentrations in the ppb and ppm, lower ppm range. The first product targeted for next year is Ozone Sensor for HVAC, smart home, smart city again. And then we want, on this technology, we want to go for further gases, NO2, CO, and so on, volatile organic compounds, and so on. To have a look into the photoacoustic platform, why is it interesting? Well, if you're in a room, you know, if you don't open the windows time to time, the air gets bad, and just because the people produce CO2 each time they exhale. This is interesting and important for well-being and for the comfort in buildings, but in addition, it's interesting for reducing the risk of virus transmission, because by exhaling, we are not exhaling only air, but virus in addition. And if you control the CO2, you can even control the risk of virus transmissions. And then it's an important matter to control the energy savings and the cost of the energy. So controlled ventilation needs a sensor to control this ventilation. This is usually outside. We have 400 ppm. This number is increasing from year to year. That's our CO2 worldwide CO2 problem. But inside a room, if you have it well ventilated, then you have something like 600 ppm or something in this range, then it's really well ventilated. If you are at a range of about 1200, 1500 ppm, then there are the first complaints that you get sleepy, frozenness, and that you can feel the poor air. If it goes even higher, you can get headaches, sleepiness, and poor concentration. And then above 5000 ppm, it really can get toxic, but this is, and above 40,000 ppm, it's immediately harmful. But we are looking more on this lower area here to control the well-being. And then Corona is everywhere. We still have it, and I don't know if this will end. But if you control the CO2, you can really reduce the risk of COVID-19 airborne transmissions. So in our headquarters in Munich, in Campion, we equipped already quite a lot of meeting rooms with CO2 sensors, really to control the air and to make the work in the office more safe. And the third aspect was the energy. And I didn't know this number, but about 50% of the energy consumed in the European Union can really be traced back to heating and cooling in private households, public buildings, and industry. So half of the energy which is used. And only about 2% of the energy is consumed, used for ventilation, so to control this, this energy of heating and cooling. And well, this amount is just the energy by smaller countries. Maybe this is quite similar picture. So how to improve the well-being at home, how to optimize energy efficiency and operation costs for smart homes and buildings by accurately measuring the concentration. And you simply need a good sensor for this. And this is the sensor we are ramping right now, our extensive path CO2 sensor. It's a real CO2 sensor ensuring really high quality data. It has this really small form factor compared to the technologies which are existing right now. It's SMD package for easier assembly, plug and play for fast customer design in, and yeah, comes with Infineon's quality and supply guarantee. How is it working? So we have an adsorption chamber. Maybe I start here with the infrared light source. So we have a black body radiator, which is simply radiating light on a broad spectrum of wavelengths. And then we have a optical filter to filter out a certain wavelength, 4.2 micrometer for CO2. That's a wavelength which CO2 absorbs. And then that's the optical filter. And then we have an acoustical detector. I told you that we are doing since longer microphones. So our detector in this case is a microphone. The filtered light gets absorbed by the CO2 in the air, and this absorption, because we periodically change the light source, the absorption periodically changes the temperature in our absorption chamber, and since this is closed, the pressure increases and decreases, and this change in pressure is detected by the acoustic detector. Yeah, the detector, the absorption chamber is acoustically isolated from external environment to avoid cross sensitivities, and the detector is optimized for low frequency range, so it's impossible. It's not a real microphone. You cannot listen to what's happening. It's really only small frequencies and which you so you cannot listen to a speech and language what's in there. And this is how it looks like. In a measurement, this is the time of a measurement in over a couple of days, and you can see that it goes up and down, and the comparison here is with so there are equivalent CO2 sensors in the market which are low cost, but they don't follow really what's happening. So the reference sensor, this is a reference sensor in the order of 2K euro, and dual channel NDIR sensors are quite okay, but they are much larger, and our accuracy is improved to NDIR. And the very important point to use it in for example, in smart home applications is that the form factor is really much smaller than what's possible with NDIR. This is again the key components. So they are all developed in-house at Infineon. There's a microcontroller from Infineon. There's a MOSFET from Infineon to drive our MEMS heater, so the black body radiator, and microcontroller I talked about, and in there's a MEMS microphone with really high sensitivity. Additional key features really developed for this product are the optical filter, to have really to filter out the 4.26 micrometer live wavelengths, and the MEMS heater for the radiation was developed especially for this product to get a high light efficiency for the electrical power put in. And the microcontroller running the compensation firmware such that we can deliver with this product really the CO2 levels and ppm level, and it's supporting the standard interfaces, I2C, UART, PWM interfaces. And that's again the slide I had before. Really, if you can adjust the fresh air supply to the amount which is required, you can really cut down this 50% of energy consumption in the European community. Needless if the temperature rise or fall due to this can be avoided due to air exchange. And with demand controlled ventilation, you can really optimize the energy consumption based on the occupancy. And to give you a short idea, it depends. Currently, the ventilation is done without knowing the CO2 content. So you have to put the air volume, the ventilation in such a way that even if a floor is fully occupied or nearly fully occupied, and on floors where only few people, you have to do the same because you don't realize how many people are there. But with the CO2 sensor, you can really do a demand controlled air volume and put your energy where it's needed and avoid waste of energy where it's not needed. And this indicates already that with such a device you can do you can detect how many people are in a room, and this works really very good. So we do, for example, in our headquarters, in the meeting rooms where we have the sensors, we can detect completely anonymously how many people are in a meeting, and if a meeting room is really used or not used, completely anonymously. Just the number of people, not who is in. Quite nice feature. And targeting, a lot of that's what we are targeting: air quality devices, consumer devices like these Alexas and others, HVAC, so home ventilation, air control, air conditioning, and smart home applications to control the indoor air quality. So to conclusion on the CO2, it enables demand-controlled ventilation to optimize energy consumption, enables fresh air supply adjusted to the amount really required, needless on the temperature rise or fall, and can create a huge positive impact on energy efficiency with respect to energy and subsequent CO2 savings. Then I would like to have a short look on this second platform, where we are cooperating with Professor Cuniberti from Dresden. It's an upcoming gas sensor family in a very small, tiny package, and what we aim for is really to have high selectivity, low cross sensitivities, short warm-up times, and what we are really happy about, and this is something MOX sensors, which are somehow established in this kind of market, we don't suffer poisoning by siloxanes. That's we could show this already. And the first sensor, first target gas is ozone, and the development is on track. And next year we want to go to the market with this ozone sensor. And one use case is air purifiers to monitor the UV emitters in the air purifier, that you don't get the ozone created by UV in your living room. So this is for indoor applications, and outdoor application is just the outdoor air quality index, where ozone is a very important gas in this index. We want to extend this sensor family to new gases like acetone, hydrogen, and other gases with additional applications. How is it working? So we have a MEMS device again with a sensitive layer on this. There's a thin film material with functional groups on it. So there's a functionalization on this MEMS, and the absorption of gases causes a change in this sensitive layer of the sensing element, and the selectivity we can gain with different functionalizations in there. And we can, what we are doing is that we use different functionalizations on one hand side, and we use advanced algorithms, AI, to process the raw data. And this heater, there's a heater below to increase the sensitivity and to deabsorb molecules we measured before. So we are convinced that our technology will really overcome the limitations of the state-of-the-art MOX sensors. High selectivity we could show for ozone already, and the specific functionalizations improve this selectivity. Our base material, what we use, is a special material, and it's unaffected by humidity. That's very helpful, and MOX sensors are suffering quite a lot on this. That's really an advantage of our technology. And there's no chemical reaction really there. There's adsorption and then electron exchange. So this really helps to decrease the warm-up times. And since our temperatures, what we use, are much lower than what MOX usually are using, we can prevent poisoning of our sensor by siloxanes. There's a lot of work in there with the material and in these algorithms to get good predictions of our air family sensors. And I think then I'm already through with my presentation and open for questions.
Thank you, Ulrich. Very interesting. And we have a few questions, and I also have a few questions myself. So shall we proceed like this? We do a few questions for each speaker, and then
yes,
I guess that's okay. So yeah, so let me start with a couple of questions from the audience. Laura Sanna asks, what about the influence of relative humidity on CO2 concentration detected by these sensors?
The frequency, the wavelength is chosen in such a way that we do not have a maybe I should switch on my my video again. No, don't know how to do. No, we are quite independent. So in the usual area region between 20% humidity and 80% humidity, there's no impact. So if you go to 0, but this is not existing in real applications, then we see some sensitivity on the humidity, but otherwise it's there's no dependence on humidity with this sensor.
If you want to go back to your slides, you can. You're still in command of the slides.
Yeah. I think the important thing is the optical filter, really to select the right wavelengths to avoid the dependence on humidity for the sensor.
And so a related question would be, so actually I have two related questions. One would be, presumably to detect other gases, you're exploiting filters that select the frequency, the appropriate vibrational frequency, suppose.
Yes. So to go for other gases, interesting gases with this photoacoustic principle, you just have to exchange the filter, and then it can go for others. But you have to keep in mind that you cannot go in the ppb range. That's too low because the effect would be really too small. And there are other gases which can be detected depending on the interaction of the absorption principles. But if you choose the right wavelengths, you can go for other gases as well.
So yeah, I also had the question, if I may, why don't you use the same principle for ozone? So this is what you just told us, that the concentration is too low to be detected.
Yes, the ozone concentration, you can smell it when it's in the ppb range, and it gets dangerous already in the ppb range for your health, and ppb is not possible with this one. Then you have to go to the other principle really to detect single molecules and catch them. Yeah.
And just a related related question. So the idea is that the absorption of the selected light by CO2, for example, is altering the pressure conditions essentially on the acoustic detector. But how about emission? Because you also, when you had absorption of, is it because the incoming radiation is directional and the emitted radiation is incoherent and omnidirectional?
So the absorption of the CO2 means that the CO2 gets the energy from the light, and this energy is transferred to the air, so mainly nitrogen molecules, and then the air warms up, expands, and you get this pressure signal. So I sometimes think we are listening to the absorption of the CO2.
Okay. I think there's a couple more questions from the audience. One says, how far is the use stay on the market of the proposed sensor for the other DOCs? I'm reading it, so maybe you understand what the point is.
Again, the question was, can you repeat?
Yeah, how far is the use, parentheses, stay on the market of the proposed sensor for other VOCs? I don't know what VOCs are meant.
VOC is volatile organic compounds.
Oh, okay.
Something, if you buy cheap furniture, it smells. And it's usually VOCs. We are going into this direction. I think all these markets are not, they are really emerging. They are waiting for sensors to give accurate and reliable answers. And currently, so the investigations on MOX sensors are since 30, 40 years. There's work on universities, and there are companies trying to bring this into the market. But all these sensors fail quite fast. Cannot really rely for a longer time. You have problems with poisoning and so on. And the markets, they are really waiting for sensors which are robust and can provide accurate readings. And yeah, that's what we are trying to do, really, to work on. There are improvements, and there is a certain market for MOX sensors, but I think we are convinced the market could be much larger if somebody could solve some problems there.
There's let's say a final question. Is Infineon developing anything about water? Or was that / will that be in the previous or next episode?
Liquid sensing would be the next step, but we are quite busy with the gas. It's really a big change for us. It's really a completely new area where we stepped in to do gas sensing, acoustics, pressure sensing. That's yeah, you have to change quite a lot of things in our labs in development. Really, to have a environmental lab is it's not that easy to control all these gases and to exclude cross sensitivities and so on. And in production, it's the same. So we are quite busy with environmental sensing in terms of gas sensing right now. But of course, then the next step would be to look into liquid sensing. Well, of course, you need different sensors there. The contact is different, and yeah. there are some ideas, but it's yeah, more than pre-development, just some thought. But that's the natural next step. Yes.
That's just a final question from me. I mean, it's just a curiosity. When I was working on nitrides many years ago, there used to be actually working sensors that revealed polar species in liquids. Essentially, the liquid was in contact with the surface of an aluminum gallium nitride, and then there was a gallium nitride below, so there was essentially a MOS, more or less, but tunable by the polarization of the upper layer. This was developed by Ambacher at the Schottky Institute years ago. I mean, I don't know if that does that have any relevance. Is that something that is pursued?
Yeah, this is closer to the what we are doing here. We use simply a resistor. You could do a transistor as well, a MOS transistor here. And right now we have the interface to gases here only. Liquids you can do in a similar way. Yes, the idea to have a MOSFET there to be even more sensitive is reasonable, but we haven't looked into this up to now.
Thank you. I think we have to
move on. Exactly.
We have to move on. So back to you, Matteo, and thanks, Ulrich, again.
Thank you.
Yeah, thanks for the presentation and the chance to show what we are doing here.
Anyway, we will take a couple of more questions. We didn't read all the questions. Maybe at the end of the next seminar by Simone, we will have also the remaining couple of questions to you. We will distribute your email to the participants if you're okay with that.
Yes.
There is, for example, Zachary Fredel who wants to get in contact with you. That was the US company I was referring to before we opened the floor to all the participants. So from the DV-Rod company. Okay, so let's move to the next speaker, who is Simone Lolli. Let me take his information. So Simone Lolli has a double affiliation. He's obviously a researcher from CNR, from the National Research Council, and in particular from the Institute of Methodologies for Environmental Analysis, which has its main seat in the southern region of Basilicata. And he also has a second affiliation with the NASA Goddard Space Flight Center, because he's there. So apart from being a permanent scientist at CNR, he's co-PI of the NASA MPLNet LIDAR network. Simone studied physics in Florence and has a PhD in physics from the École Polytechnique in Palaiseau, France. He is a visiting professor in Spain at Universitat Politécnica de Catalunya, and as well as at the Kent State University, KSU. So we saw now sensors based on solid state or photo emission, and he will present us different kinds of sensors, of environmental sensors, which are sensors for aerosol, cloud, and precipitation, and he will detect this. He studied this aerosol, cloud, and precipitation by remote sensing techniques. I insisted, or say I asked him, more than insisted, I asked him to also give a brief overview of research infrastructures in which he and the institute he's working is involved, which is the Infrastructures Actress, which is part of the European research infrastructures. and actually stays for aerosol clouds and trace gases research infrastructures. Actually, this infrastructure is led by CNR and is dedicated to accurate ground-based remote sensing measurements. Okay, so the floors is yours. Let me
okay.
You moment.
I think so. I hope it's in full screen right now. And so thank you very much for the very detailed introduction, and I'm very pleased to be invited as speaker for this webinar between Germany and Italy cooperation. So let's start. So if someone is choosing like a healthy lifestyle, there is something that is not, let's say, under control. So what's going on? So breathing. So doesn't matter where you are. So, and you need always to breathe. And considering then the fact that most of the population live in a large metropolitan areas, so many, very huge percentage of the population is subject to bad air quality and cannot avoid, unless you're living in a smart house with all. So also we saw from the previous talk. And during this talk, mostly I'm going to show some techniques to study mostly aerosols and their effect mostly to air quality and climate. These are interconnected. But if we go more close, so what we mean by bad, for example, air quality. So bad air quality just means if a clean atmosphere is an atmosphere where just, for example, nitrogen and oxygen and other few trace gases are present. But instead, we have tiny short-lived particles that are suspended in the atmosphere. And those kind of particles can be both anthropogenic or man-made or natural. So those kind of particles, what they do, basically they scatter and they absorb the sunlight, and also with the extinction. And this is how it works. So we have a sort they reflect the incoming solar radiation, and also they can be emitted primary or created to chemistry. So you see here, so a kind of a CO2 that is going from chemistry is transformed into aerosol or produced directly by soot or dust that is a natural source. And also they act for a chemical reaction to take place. So the importance of the destruction of stratospheric ozone. So remember, ozone in the high is good, ozone at surface is bad. And mostly, so those are we can see like a big difference in between. So aerosols are very different. So we said that there are anthropogenic aerosols, and those aerosols are very different also in size. Like they can span from 10 nanometers to microns, and also the IPCC report that aerosol introduce a large uncertainty in the global climatological models. So if you're not familiar with aerosol, but familiar, for example, with maybe you heard about the PM 2.5, particulate matter 2.5, PM 10. So for example, here PM1 are all those aerosols that have a diameter that is less than 1 micron. So here is 1 micron over here. So the 10, so we have this. And all these aerosols, they are short-lived. That means that those are not the CO2 that is last a lot in the atmosphere, but those kind of aerosols stays like for weeks or maximum months or days. So you can see here, so and those the type of aerosol have also different functions. So they start from nanoparticles. You have soot, then you have like mineral dust, volcanic ashes, and then pollen, bacteria, spores, and then up to the cloud droplets. So, and also, I'm not going into detail, but those aerosol are also responsible for different types of physical phenomena that can be resumed as condensation and coagulation. So this is here the picture. So there are the different stage of the different aerosol. So by model simulation, and mostly so the aerosol affect climate, so the earth and the atmosphere, energy budget, so air quality, and more that the human health. So as I said before, this is not possible to avoid breathing. But let's go more, which kind, so which aerosol species? So I bet you are familiar, so especially in the Southern Europe, because like in Germany is much more unlikely to have. So if you are going to pick up your car and it's covered of dust, so this is because dust aerosols from Sahara region are advected, so from this source into our latitude, so through the atmosphere again, then to the surface. So we have dust, so we have a sea salt, so we have a sulfate, black carbon, so organic matter, and nitrates. So those are all the different kind of aerosols. So, and another important distinction to do is the type of aerosol. So can be like a local or act as a background, like a traffic exhaust, or as I said before, advected, like dust when it is a vector, or for example, during a volcanic emission. So those are how it look like. So, and then we have here sea salt. So because of waves, so the sea salt, the spray waves are generated into the atmosphere. And those here, what we have, so we have like a microscopical vision of the different type of ashes. So as you can see, the shapes are pretty different, like from pollen, so it was more spherical, or like volcanic ash that is very unspherical, and also the soot over here. So here I'm going to show to you, I hope it works. Okay, maybe. So I will show over here. And this is like, I will put full screen. So this is a simulation. So from the model, so you can see in white the smoke, then you have a sea salt, and then you have dust. So this is a simulation that ran into, so in 2017, so it's the month of August. So whether you can see here, so you can see like wildfires that are originating into, so in Canada or in California. And in the blue one here, you have the sea salt. So you will see, keep going watching, so you can see also like cyclones originating, and they are full of sea salt. So, and the most amazing here, you have the dust outbreak. You can see, so this is called the dust corridor, or how dust from generating from the Sahara Desert is reaching, and the like South American and North American, besides Europe. So, and what is important to stress over here is that how all these particles, for example, react, so for example, for climate, and also like dust, for example, when it is advected into our latitudes, is dust, for example, dangerous if we are going to inhale or breathe dust? For sure, smoke it is. Dust, there are other studies that are confirming that inhaling dust can bring so to different kind of disease. Like here you can see now they started some wildfires in the northern of Iberic Peninsula, and so on. So this is full almost 6 months of simulation, so from NASA. So these are okay. I'm going to, okay, that's already done. I back to the presentation. So, and this is what we have here. So this is the different aerosol, but also those are very important for climate, because as you have a blanket or like an umbrella, so it can be both. So the aerosol can be reflected from the solar radiation or can absorb. For example, black carbon or snow is what is accelerating the climate change, because the black carbon is absorbing a lot of solar radiation and heating much more and contributing to melt of ice and snow. And for example, other sulfates instead are changing the albedo of the Earth, and they are cooling the system of the atmosphere and the Earth. So as you can see here, so there is not so much uncertainty for trace gases like CO2, so for carbon dioxide or methane, but for aerosol, there is a lot of uncertainty. So for this reason, also the IPE, so the Intergovernmental Panel for Climate Change, state that aerosols are one of the more important sources of uncertainty into the model. So for this reason, also besides because they are detrimental for air quality and climate, so this is important to have studies. So this kind of short-lived particles. So this is also influence the cloud formation, because aerosols can function as condensation nuclei. So for this reason, they can produce more, for example, more droplets. So a bigger number of droplets, and then for this reason there is no condensation, and so they are inhibiting the rain, or they can do in the opposite direction. So they can inhibit or enhance cloud formation. For example, in places that are very clean, like at Arctical latitudes, they can start to produce and work on enhancing cloud formation, because cloud formation is really helped by aerosols. And so this is China. So this is just an effect of aerosol. So if you are in the bad place and a bad time, so if you see here, this is 13th of December 2015. So the brown over here, see the brown. So just breathing means that you are smoking 25 cigarettes. So this is the cigarette equivalent of bad air quality of breathing. So you have, so in these places here, just for breathing, every 24 hours, you are like smoking more than a packet of cigarettes. And also you see the baseline, so I'm not going into detail, but especially for countries as China or India, this is a link to the life expectancy decrement, like it can be more than 2 years, so if you look here. Hopefully for our latitude, so we have a strict regulation for emissions, so that we have a much better situation. And the European threshold should be like for PM 2.5, should not exceed daily the average 25 micrograms per cubic meter. So there was a picture that I took in 2019 when pandemic was not still there, if possible to travel. So, and this is what I saw approaching Shanghai in China. China, they are doing a really great job because they are implementing technique, and they are really trying to decrement emission and have a much more better air quality. But you can imagine, so you cannot avoid, instead you have a mask or something like that. So breathing into this kind of air. And there are some quick facts about air pollution. So, and like an adult is consuming around 11,000 liters of polluted air every day. So this is unavoidable. And so we saw the different sources of pollution. So the vehicles, so the traffic, they are like 60% of carbon dioxide in the US. So we have also 95% in large metropolitan areas. And this is just in London, the Great Smog in 1952. There was killing more than 4,000 people that are attributed to this extreme event of bad air quality day. And also you can say that, so from Harvard Public School of Health, 4% of all the death in the United States can be attributed to air pollution. So this is, for this reason, is also so very important. So those are the air pollution. So we saw before, so oxons or carbon monoxide, carbon dioxide, also nitrogen, so the VOC also. So those are all the different types of air pollutants. I'm not going to skip. So this is how it looks like. So if this is a human hair, so it's a 70 micron. So those are the dimension of those particles. So this is PM10, so those bigger here, and then the 2.5 are those kind of particles. This is a fine pitch sensor to have a reference. So this is the size of those particles. For this reason, it's very difficult to have a study. So, and then as I said before, ozone is good when it's up high and bad when it's nearby. And this how, so what is important, it's to see how for example, ozone formation at surface, so that like the pollutants bake together in direct sunlight forming ozone. For this reason, like during the summer, we have ozone level that are much higher because of this chemical reaction that is using the sunlight. So the more intense is the sunlight, the more ozone is produced, like with the NOx, the VOC, and then you have ozone formation. So those are carbon monoxide. So we should revise and have our policies for have a green metropolitan areas, reducing maximum the traffic and using public green transportation. So those are, as I said before, so we can skip. So as I said before, when the air pollution coming from, so we have wood burning, fireplace, and burning toxic substances. Plastics, this is very extremely bad, like because it's also producing dioxin that is very toxic. So also here in Italy, we have a lot of land clearing fires. They're very bad. So it's like obliging population in living into a smoking room. So you experience if you don't live exactly in the city. So during from like in the spring and at the end of the fall, you have a lot of this kind of land clearing fires. And also air conditioner, refrigerators are also producing, fire extinguisher, fossil fuel burning, car, trucks, ships is a lot of pollution. So they're like marine environment, cities, they are experiencing a lot of pollution from ship traffic. And then also, of course, households, so hairspray and the air fresh. So those are all the different different types of air pollution source. So, but again, so I would like to take home messages like air pollution is strictly interconnected with climate change, because also those kind of aerosol are injected into the atmosphere at a higher level or higher altitude. So, and so this is what is, and also you have transboundary pollution, because this is not just a national issue, because if you live in a country that it has like production of a lot of pollution, then for the meteorological, so to the meteorological circulation, is this kind of pollution is advected into neighbor countries. So they have downtown, so they have also of these sources. So, and let's take more. So now we go to the remote sensing, and we are going. So this is a mission that where I was involved. So this is a NASA mission. It's called the 7 Seas mission in Vietnam. So you can see. So you can study aerosol under. So that you can study the aerosol, for example, optical properties like here, or you can study, or you can measure, for example, their concentration. So because the light is influenced by what you have in the atmosphere, so where the air, so you can see here, so the AOD is called the aerosol optical depth, so it's the optical depth of the aerosol. So if you don't have aerosol, this quantity will be 0, but then is like, so 1, so you have a pretty good visibility. And here, so you can see if the AOD is 2.7, it's not possible, so you can see anything. So just for your reference, when you see a cloud, so the optical depth of the cloud, when it's higher than 3, you will not see, you cannot see the sun anymore. So this is how it is. So this is another picture. So, and you can relate exactly the aerosol optical depth to the concentration of pollutants. So we have here different pollutants from 8 milligrams per cubic meter up to 278. So you can see here how the visibility is degrading with respect to a lot of concentration of pollutants. So you can see here is nothing is visible. So the background is no more visible. And of course, so this is influencing the climate because for example, sunlight are blocked to arrive to reach the surface, and also you breathe this kind of air. So this is Southeast Asia, for example, is an open air lab where you have a lot of aerosols. So you can see like a residual burn, forest fire, wasp fire. So you can see clear day again and haze day. So for PM 2.5, you have 10 here and 150. So you can see here there is no more possible to see all those mountains in the back. And this is what, so this is a mod. So you to tackle the problem of aerosol, you have to use different techniques. So you have like remote sensing, ground-based techniques that you are going to see in a while, and then also you have models. So this is like August. So for this is a model that shows to you all the different sources. And so this is the biomass burning. So here in red, how during the fall season, during the burning season. So you can see that most like at least 7-8 countries are touched by the problem of this is so this smoke that is traveling around into different nations. So if you go more, so then we see also the more project that I'm involved as the National Research Council. So we are using so to study aerosols, for example, to study optical properties and geometrical properties of aerosol. So what we use is the remote sensing. As a definition, the remote sensing is the acquisition of information about an object without making any physical contact. So that means that you are, so there is a medium that you are they get information. We can divide those kind of sensors like active sensors, so the active and passive sensors. So the active sensors are, they use a pulse and then are retrieving properties, optical properties, so for example, aerosol, using the backscatter energy, and the passive sensor are using the sun as a source. So in this reason are like taking the reflecting lights. These are the main two differences. So we are now going to see all the differences, the different technique that we are using in the frame of the MPLNet and the Actris research infrastructure. So I'm not going into detail. So this is a LiDAR remote sensing. So just because the conservation of energy, so the transmission of, so the LiDAR, if you are not familiar with LiDAR, it is an instrument that is using as a source to monitor and the atmosphere using a laser source. If you want to see it, is a sort of radar, but instead of having a microwave or an electromagnetic waves, is using light as a source. So you can see then, I'm not going to do it, and then it's sensible. The backscatter energy is related to the molecular absorption, scattering, and aerosol scattering absorption. Of course, if you have also cloud and precipitation, they will be sensible also to those here. So, and there was so a lot of LiDAR missions that we see later. So you can see, so I was working also in a private company for 5 years. They were making this kind of manufacturing LiDARs for small portable. There is also NASA mission that is very successful, Calypso, and those are other tips of LiDAR. And this is an inverse problem. So I really like this kind of animation from from this kind of picture from my colleague Landulfo in Brazil. So you can say that solving like the LiDAR is like solving an inverse problem. So you have the footsteps, and then you should know which kind of aerosol you have. So it's sort of like, you know, you have a dragon and you have which kind of footstep is present. So this is how it works. So this is not direct, this is indirect. So this is like an inverse problem. So from LiDAR, so from the backscatter light, you have to assess, for example, which kind of aerosols in the atmosphere and how much they are. So this is how it works with LiDAR. So to have an example, so mostly, so this is what also it was, I think we have studies, recent studies from actress community that I will show later. So this is, so here this composite plot is showing, so here we have, this is the altitude, this is the latitude, and this is time. So all those different pictures are showing, for example, how we detect how, so from Australian wildfires are injected into the troposphere. So you can see here into the stratosphere. So, and as you can see, so the ejection is in the troposphere, and then with so in in 3 months you have that. So here you have the altitude, and so in this latitude here you have that the fire plume is at around 30 kilometers. So of course this is influencing the climate. So this is the same, and this is done using the Calypso mission that have a LiDAR into satellite. So you can see here how like the smokes from the troposphere is injected into at higher altitude. So here we have another one. So we have the Canadian wildfires and Piracy B. So Piracy B are those kind of clouds that originate from wildfires. So here again, this is from Calypso. Calliope is the LiDAR on Calypso, and here is the tropos. So the tropopause is here, so you can see how so the fire and the smoke is injected into the stratosphere with a lot of implication for climate. So this is a LiDAR in Thailand we used during some measurement campaign. So it's not Photoshop. So we use 532 nanometer LiDAR. So this is green light, and this is in Vietnam. And so those are some pictures from images taken in the on-field measurement. Then, so we saw, so this is to study what we use to study aerosols into the atmosphere. And this is a very important because this is the LiDAR with respect to all the other techniques can give to you the vertical profile of both the geometrical and optical properties of the aerosol. Another important instrument is the NASA mission is the sun photometer. So because from the radiative transfer model, so you know the energy of the sun, you know the distance, you know exactly how much energy you should receive at your instrument. So for this reason, if you the more aerosol you have, so in this layer, so the more you can retrieve aerosol optical properties. So you have the AOD, so it's the measure of the amount of light that scatter aerosol and absorb aerosol in the atmosphere. So and the prevent generally the sun shortwave radiation from reaching the surface. And again, the AOD is a surrogate or a proxy for PM 2.5. So we can use also this AOD, for example, we saw it later, so in a few moments, like to see how to monitor the aerosols and the pollution from satellite. So this is to have an idea. So this again, NASA missions these are all different measurement stations, and so this is a milestone aeronet that was given for studying the aerosol because they give a very long, more than 20 years of measurement. So now if we go to the aerosol cloud gases and research infrastructure, so this is an European project that is led by Finland, but is the PI is in my institution at IMAA in Potenza. So we have this is a research infrastructure. This is with respect to before. So again, it's a ground-based research infrastructure where you have, of course, LiDAR. So LiDAR started with LiDARs, and you have also a lot of other instruments. So you can see also, this is not an interactive map, but if you go in this address here, you can see how it works. So, and so now I'm a little bit running out of time, so I will be more fast. So you can, so those are the main principle of ACRI. So it's exploring the atmosphere, is a long-term measurement of aerosol cloud and trace gases, and those are collected by the surface and to the stratosphere. Again, as I said before, from some recent studies from ACRI, they were showing the wildfire, and what is important with respect to other techniques, or like the other one where I was showing before, like the micropulse LiDAR network for NASA, or the Aeronet. So it's ensuring high class and quality measure assured data. And so this is this instrument are very sophisticated. They give the best accuracies possible for aerosol study. It also is easily accessed data, so it will be available to all the community. So if you are more interested, so if you have the slides, so you can go and click. And if you get this map, you can click on the map. You will see all the different facilities that you have. So this is research infrastructures in the frame of the ESFRI Scientific Forum in Europe. Then, so this is an example, so courtesy from Lucia Mona, my colleague. So here, so you get, so there is a huge work to make operational ACTRIs, and this is how, for example, measurement from California fire, that this is the fire detected by LiDAR, are, for example, injected into the SEMWF model, and so there is a science task in progress where all the data that are measurement in near real time will be injected or assimilated by the model. So you can see here how it's changing. Just so, and this is important to say, this is just one site that is assimilated. You can see how, so then the models are changing with respect to this assimilation. So this is a working in progress, and there will be probably have so one of in the few years. So in the next few years, will give a lot of important scientific implication. And so this is another study where I was involved too. So it's from Calypso. We take so again, so go there. So we take two regions. One, so they were very prone to climate change and air quality problems. So those are the Po Valley over here, and then is the Benelux area. So those two are very prone to bad air quality because of mostly the Po Valley. It's because also of the orography, because it's in between there is a lot of industrial plants, and then you have also mountains. So this is making difficult to aerosol to escape. And so we were not going into detail, but we make an analysis using LiDAR data over almost 10 years. So what we see is that we have a decrease. So there is a decrease. So these are the you can see I'm not going. So this is the AOD. So the up. So the more the huge it is, the more pollution you have. So you can see that you have a drastic reduction of AOD, and that what is good for LiDAR, that you have the vertical dimensions. You can see that, for example, here you have a bump, so you have more aerosol at 2 kilometers, but that's good for air quality because you are not supposed to breathe at this altitude. So you can see that all the European policies on reduction were working, but this is not enough. So, and we compare this intercomparison with a clean region like the Sahara Desert, where there is no anthropogenic activity. So, and we show that the anthropogenic, so the aerosol emission reduction contribute to raise air surface temperature. So this is something contradictable, and cannot be a very, so it can be taken a dangerous way for decision maker, depending on their view on politics, because if you have a cleaner, so if you have a cleaner atmosphere, there is more heating of surface temperature. So they can say that if you polluted more, you can help climate change. But unfortunately, this is not the good way to do it, because of course aerosol. So we saw before that these aerosols are reflecting the incoming solar radiation. Then we have other European. So this is MODIS. So MODIS can give you an overview, but 10 by 10 kilometers of the pollution around the world. And so this is
Simone,
what
just
you have.
a few minutes.
No,
just
I'm done.
minutes.
I'm done.
Okay.
Yeah, I'm done. So you can use this kind of satellite remote sensing. So you have MODIS, you have pollution here, the hotspot. And then, so you can use also high resolution satellites. And this is like a map. So it was still in Thailand. So you can saw those here. The red spot are where there is most of the smoke. And you have this is on 30 by 30 meters. So you have pollution. So this is very useful if you want, for example, to monitor pollution in urban environment. So there is then again ESA Copernicus Sentinel mission. Those are the same. So to have European monitoring of air at European level. So I wanted to do maybe to go here and have this. So this is how it changes. Those are NO2. So this is a pollution. How this pollution decrease during the COVID outbreak because of few emissions. So this is from satellites. And if we go to the future, so this is spatial perspective, we will have geostationary satellites. They are going to monitor in real time pollution, geostationary, that you can have like an image ever. So Tempo will be launched in the 2023, and the Sentinel-4 and GEMS are already sent. So there will be like a constellation for the Northern Hemisphere to monitor pollution. So we saw that pollution and aerosol emission are both interconnected, and we have that the only way to tackle and the study aerosol is to have a synergy between different remote sensing technique, and then also interdisciplinarity. So it's the first from NASA that is going to work close with epidemiologists and health organization to set up some mission to study human health and improve life. So this is for the MPLNet stuff, and then also from all my colleague knowledge in IMAA-CNR. Okay, so maybe I put my camera on.
Yes. So thank you very much for the detailed, fast-paced overview of a lot of environmental related say snapshots. Let's see if there are questions. Allora, okay, Vincenzo already answered a question about the slides. So as I told at the beginning, you can download them directly on the right from documents. But anyway, I will send links so that you can download them afterwards as well to all the ones who register. So the one participating today and the one who were interested but didn't make it. Okay. Actually, I don't see questions, at least for now, for Simone. Okay, there is a couple of questions for Ulrich still pending, but for Simone, let me see. So you told us about Actris, and you told us about NASA, at least one NASA project. Then there was Copernicus. So there were several remote sensing, let's say, endeavors for measuring, what I understood are similar things. So how do they differentiate? Are they superposed?
No, actually, so as I show in the presentation, those are interconnected. So you have air quality and of course climate change and climate, and there are in US and in Europe and in Italy we have Earth observation missions, so that you have from NASA, the MPLNet, or all of these like MODIS, those are related to the NASA Earth Observation Program. And the correspective of this program is Copernicus in Europe, that is managed by the European Space Agency. And under those umbrella, there are also other kind of projects, so, and also, of course, ACTRIS. So, and under the Earth observation, what you have, so you can have observation from satellite, and of course you can observation from aircraft, observation from ground-based instrumentation. So ACTRIS is below, so is under ground-based observation, and so it's monitoring constantly with the high quality measurement, all the different aerosol, optical, microphysical, and geometrical properties of aerosol, or also clouds and trace gases, because those are all interconnected. Maybe it does it answer. So those are parallel programs. Of course, they have also some different. So they are going together. So they have like common points, and so they also collaboration. But for example, US and Europe, they developed their own Earth observation programs.
Okay, so let's stick, for example, to Europe. So ACTRIS and Copernicus, how do they complement each other? What is done?
No, Copernicus is like Copernicus is doing all the different Earth observation programs. Like you have a program that is called Sentinel, that is the main objective is to have a multispectral satellite that are orbiting the Earth and having measurement from satellite. And ACTRIS instead is a research infrastructure that is still observing the Earth, but observing the Earth from the ground and providing, for example, measures. So those are punctual measurement. Because satellite, you have a global vision, but ACTRIS, for example, you have different stations at different places. Like we have, if you go to click on the link I provided you, so you can see like. You could say Potenza, there is a suite of instruments to study. Then you have also in Germany, you have in Spain, and all those are providing measurement at one point. The satellite mission instead are providing the measurement at a global point of view. So there is a different scale.
Okay, so there is a detail from ACTRIS at the local level, and let's say less detail, but more coverage with the other one.
Exactly. So the satellite is given to you, like you can have, for example, an overview of Europe or Italy or Germany. And ACTRIS, for example, is a punctual measurement at ground station. So you have news where is exactly located the research infrastructure.
Okay.
And then, of course, there is validation from ground to the missions. Like, for example, ACTRIS will be used for another Earth care mission from the European Space Agency to measure, for example, again, aerosol from space that will be launched in the next 2023-24, but still to go. So, and these ground-based measurement are then validating, for example, what we have from satellite measurement.
Okay. Right. So if you have questions, you can still ask them. Before I get Ulrich, are you still there? I don't.
Yes, still
you,
here.
you are there. Okay. So before I come to you with the last really two questions that were haven't been asked before, And before everybody leaves, I would just remind everybody that this is the second of a series of webinars. The next one will be in a month, and now I don't have it here. I thought I had it. No. Anyway, it's in May. Sorry, I was convinced that I had it open. So it's on May, no, April, sorry, April 6th. No, April, okay, April 6th, which is a Wednesday again, exactly before Easter. And it's dedicated now. I'm sorry, I have to open the file. I opened the wrong one. So let's go to the question, and then I will find the right file. The question is from Strambini, Lucanos Strambini, and he said he returns to the humidity interference. He says humidity and room temperature are very strong interfering agents for each gas sensor. In the case of the extensive sensors, he says no room temperature and humidity sensors are provided, and any kind of compensating strategy. So this is more of a question probably. In my opinion, the environmental condition of the environment on the sensor absorption chamber is affected by room temperature and humidity, and in turn the sensor performance. So again, he asks how you manage to say eliminate or reduce the interference from humidity and room temperature.
There's some compensation algorithm in to compensate for slight humidity dependencies in there. It's a question of the frequency you use with which the light source is running, but in the end the humidity dependence of our sensor is really low, and it's not a problem for us.
And the temperature, so the room temperature?
Yeah, we have a temperature sensor in the device, and it's compensating for temperature.
Okay, so you have that. Okay.
Yeah.
I see. All right. So now I found. I'm sorry. Now I found the document with the next seminar. So with the announcement that you will receive in a couple of weeks. So as I said, it's April 6th. The title of the seminar will be Novel Functional Materials for Biosensing, and we will have, as always, two speakers, one from CNR, which is Vincenzo Palermo. He's actually the director of CNR Institute for Organic Synthesis and Photoreactivity. And on the German side, we have Andreas Tittel from the Nano Institute in Munich, so in München, of the Ludwig Maximilian University in Munich. So that's for the next webinar, and then we will go on in May, but we still have to fix it. Okay, so is there another question? Okay, the same person asks if there are scientific papers with data on your sensor performance. So can he read results, experimental campaigns with your device?
There's a lot of material on the Infineon side. There are data sheets on it and things like that. So I can provide if he contacts me.
Okay, so he will get your contacts and he can write you directly. Okay, Vincenzo, am I missing something? Oh, there was one, yes, Maria Sileo, but she left. Okay, so she was asking, some sensors measure CO2 equivalent. It can be equated to CO2. What is the difference between CO2 and CO2 equivalent?
They try to find correlations. It's again in the direction of MOX sensors, and they claim that there are correlations to other gases. MOX is not sensitive to CO2. That's a problem for the MOX technologies, and they try to find correlations. But these, when we test them, and they are, it's not only us. We see that there are some signals they don't see, and they have artifact signals there. So sometimes the correlation works and sometimes not. That's the problem.
Okay. And then there was a question which was already asked, I guess, but maybe I mean, at least me, I didn't really understand. Yeah, I think Alessandro Bellucci had asked how far is from the market, from the possibility of buying the sensors, your sensors, for other VOCs. So you can buy already your sensor tuned to CO2. Did I understand? Yes. Okay, so his question then, as I understand it, how far is the use in the sense of the possibility of buying on the market your sensor technology for other VOCs?
Yeah. So I think so. The interest for VOCs is again in the low ppm or ppb range. That means our second technology, the absorption based technology, and there our first one will come next year, and to go for VOC this will take longer.
Okay. I
don't know, 25 something. Yeah.
Okay, so and the first one would be ozone then, or
yeah, the first one is ozone, and NO2 will be the second. That's where we are working on heavily, and yeah, we will bring them to market first and learn and then expand our portfolio. And we will publish on our Infineon Home websites what we are doing.
Actually, as I saw, there was already an explanation, but I want to in your slides. But I think it's an important point, so I would like to reiterate. I'm coming from the sensor business too, actually, and one problem with the MOX sensors and with solid-state sensors is that these gases interact with the surface and modify the surface. And so they stick, and if you want to, and if you heat up the surface, they may go away, but then the surface modifies itself as well. So what is measuring after is not the same device that we're measuring before. So this is my, let's say, experience from the past. So how do you counteract that?
Solve this problem. That's what you know from your nose as well. Huh? If you get a lot of pepper in your nose, then you're blocked for a while, and you have to sneeze and to clean it again. And essentially, that's what we are doing as well. So one important point is that we go for lower temperatures, really low temperatures to avoid chemical reactions, and that our sensitive layer gets changed. And the other point is, yeah, that we have ways to desorb again the molecules to get to a virgin state again. And we have algorithms behind. That's the three approaches we are do to tackle these problems. But of course, it's not easy and to do this, and it's a different, really different technology to compare to the photoacoustic. The photoacoustic is clean. You have to see there's really no interaction, just the light with the CO2. That's much better. In the adsorption type technology, yes, we have a contact, and of course this is a threat, but we could show, for example, with Silan, which is a very common problem, that poisoning occurs with Silan, and this works fine for us. But of course, you can somehow destroy the sensor if you put. Ozone is quite aggressive, as Simone explained already, and it can destroy everything. It's just a matter of time, and then it destroys it. So these sensors will not stand forever. But if you have a sensor working 5 years, it's great. There's no sensor like this outside which can work for 5 years.
That was my next question. So for how long do your sensor resist? So up to 5 years?
Yeah, that's the target where we want to go to. So if you think about your mobile, if it stands 2 years, you're happy. So that's in the consumer quite okay, but that's really the lower limit. 5 years. There will be so much development within 5 years that probably you're happy to buy the next sensor then. So it's not the automotive range, 10, 15 years. That's, I think, not really needed.
I see. Okay, from my side, I don't see any more questions. Vincenzo, am I missing something?
No, I think.
No. Okay. So anyway,
No,
it's 10 to 12, so I would say that you did your job. Let's say. Thank you very much for I think the presentation were at the right level to be understood by a broader audience. This is the sense of this series. So it should not be only for the persons working in the field, but for a broader audience. With the idea, we had already a case in which the people from the network, from the CNR researchers, can interact with the speaker afterwards, having seen what he's doing, and and the few Germans that were participating obviously can do the same with Simone. And so from my side, that's all. Thank you very much. The last words, I leave them to Vincenzo.
Thank you. I have nothing to add. It was a pleasant morning, very interesting. And so see you on the 6th of April then, and have a good day.
Thank you very much.
Thank you to you all. Thank you.
Thank you. Thanks.